Let's take a look now at example number 5. And this one's slightly different than some of the examples that we've seen before. Because notice I'm not being instructed here to find a most general antiderivative. I am being asked to find the function f that meets the following two conditions. I'm looking for a function f whose derivative would look just like this, but also when I plug 1 into the f formula, I generate the value of 3. Okay, so to start with this, I'm going to try to find the most general antiderivative, at least just to start. So I'll state here that we note that f of x could be equal to something like the following. I could just start by doing my antiderivative of each individual term, and let's see how this would work. Notice I could have x would be raised to the 6th power, and then I could do 3 divided by 6. Or, if I wanted to, I could go ahead and just rewrite that as the value of 1/2. Notice again, everything can be double checked here very quickly. Just take the derivative of this. If the 6 comes down, it's going to be 6 times a half. That will be 3. And then my power will go down to the 5th. So this here works perfectly. I can do the same thing here. I know my power is going to go up to the 4th, and so I'm going to divide everything in front by 4. So I could also write that as 2/4 or a half. Again, I can double check with the derivative. Over here, my power is going to go up to 2, so when that 2 multiplies down, I could put a 3 there. 2 times 3 would create the 6. And then I can get an x to create the 1, and finally, plus c. So this is what my function could look like. But now I have to account for the fact that I've been given that when I plug 1 into this function, I'm supposed to get the answer of 3 out. So I'm going to go ahead and state that we now use the fact that f of 1 equals 3 to determine the exact value of c needed. Right? There's going to be some number here at the back to make the correct f function, but I'm going to use this to help. So here's how I would do it. I note that if I was to write down my function here with a 1 plugged in, that would look like 1/2 times 1 to the 6th, and a 1/2 times 1 to the 4th, plus a 3 times a 1 squared, plus a 1 plus a c. That's what it looks like if I plug in the value of 1. And of course, when I do this, I'm told that all of this should actually turn into the value of 3. So notice that when I make this replacement then, I actually only have now an equation with 1 unknown. The value of c is the only thing that is a mystery. So let's try to simplify this down. On the left side here, or sorry, on the right side, notice I'm going to have 1/2 minus a half plus a 3 plus 1 plus c. And so let's see, my halves are going to cancel. I could subtract 3 from both sides. And then if I subtracted 1 over to the other side, I would end up with c is equal to -1. So that means that I can actually state the exact function that meets these two properties. F of x would be 1/2 x to the 6th minus a half x to the 4th plus a 3x squared plus the value of x, and then instead of writing plus c, I can do plus -1, or just -1 also works. There it is. And again, the great part here is that I can always double check my work. If I take the derivative of this function, I should get f prime. And if I plug 1 into this function, I should get 3. Now, we already set things up to make sure that we were doing that along the way, but if I was ever unsure that maybe I made a mistake or I just wanted to double check to be sure, I can easily just double check by plugging in 1 or taking the derivative. So problems like what we see here in example 5, and actually in the motivating example where we were also given a derivative and this kind of extra piece of information, are commonly referred to as initial value problems, because I'm given some initial value about what the function turns into when I plug in some value at the start. So we'll see different initial value problems fairly consistently throughout this section and the sections to come.